All right, in the past, when we did integration, it was really obvious. It was, this is what you're seeing, so integrate it this way. Or it looks like it's a quotient rule, or it looks like it's a product rule, or it looks like it's a chain rule, so that means automatically you do U-substitution. What we're doing now, this next unit, is we're looking more at different types of things we're going to be integrating where it may not necessarily be super obvious how you integrate it, and now we're just learning different techniques that we have for integration. So I'm going to give you ideas of what to look for, but I can't tell you it always works out this way. So that's what we're going to have to start getting used to, is we got to do a lot of these so that we can start to get like an intuition for what method we can use depending on how we see the problem. Okay, so one of the techniques we're going to learn today that is new to us is called integration by parts. So integration by parts comes from the product rule for when you find a derivative. So the product rule for derivatives if you recall, you would have two different functions that you're multiplying. That's what we mean by product rule. So we might have function u multiplied by function v. And if I take the derivative of that, that would be the first function times the derivative of the second, plus the second function times the derivative of the first. So if I take the product rule and I go back and I integrate that, I'm going to integrate this side, and integrate this, and integrate this. I can split these apart because that's one of my properties of integration, is that in an addition problem I can integrate those two things separately. If I take the integral, or if I take the antiderivative of a derivative, then I just get back to the original function, or in this case I would get back to the original product of functions that I'm talking about. And then I still have the integral of u dv plus the integral of v du. And then what I'm going to go ahead and do is I'm going to subtract over this v du. So I'm going to have the product uv minus the integral v du, and that equals the integral of u dv. So this is the formula that we are going to be working with for us to integrate by parts. It does not make a lot of sense now, and it probably won't make a lot of sense until we get a ways through the video and you see a few examples. But this is the formula, essentially, that we are using. So here, when we do integration by parts, this is what we're using, and it only works if u and v are functions of x with continuous derivatives. So the things that we looked for before when we were doing derivatives, we're still going to look for. The function has to be continuous, all of that stuff. All right, now like I said, I can't say this unit, it's going to work out this way every single time. But my goal is to teach you some strategies that we can work with. So the first hint that I'm going to give you is the acronym LATE. So here's the acronym, L-A-T-E. If the function is a logarithm, if it is algebraic, if it is a trig function. When they say algebraic, I just realized as I'm writing this down, I don't even really know what that means. I think for algebraic, they mean like polynomial. I should look into that for you guys. So logarithm, algebraic, trig, and in this case, we're going to include inverse trig and exponential. If you see any of these functions first, because when we do this, you're going to be looking at something where it's two different functions that are being multiplied together, and you're taking the integral of it, and it's not one where a typical U-substitution would work. So when you look at these two functions, The first type of function that you can see, if it appears as one of these, you're going to define that as your U function. You're going to find this as your U function. Everything else you would call as your dv function. So I'm going to say the first type of function Again, it's okay if these notes don't quite make sense yet. After we do a few examples, then it will be helpful for you to go back and have this written down because you can refer to it later, all right? So like I said, this doesn't always work. This is a strategy that will often help us. So for all of the examples that we're going to be doing, the instructions would just tell you to integrate. So integrate all of these. For the first example, we're going to find the integral of x times e to the x dx. So if you look at this problem, it appears to be a product rule, right? We've got two things multiplied together. When I look at this, I can see clearly that U-substitution would not work. And so that's how we're going to know, all right, integration by parts is my only real option. So the first thing that I'm going to do is recognize what I should have as my U. And I'm going to use x right here as my U. The derivative of U, or the derivative of x, is 1 dx. And so now what I'm going to do is call the rest of this, so I'm taking away the x, the rest of this is going to be considered my other function dv. So dv is e to the x dx. So from my formula, I have u and dv figured out. Now, since I've got dv, I have to also know what just plain old v is, and that is the antiderivative, or that's the integral of that. So I need to think about what I would get if I integrated this. The integral of e to the x is still e to the x. All right, so now we're going to fill this out using our formula. So I've got u dv, that's already written, equals u times v. So u times v is x times e to the x minus the integral of v du, and du's over here. So times 1 dx, or just times dx. All right, now I can ignore all of this, and this is the problem that I'm dealing with. I've got x, e to the x. If I integrate e to the x, that gives me e to the x. So e to the x plus c. All right, that one's all done. For our second example, we're going to be integrating x squared ln x dx. And again, I'm thinking of LATE, that acronym, and I need to recognize what my u is. So here I see a logarithm, or in this case a natural log, and I'll go ahead and use that as my u. So I've got ln x as u right there. And then I need to know what the derivative of u is. The derivative of ln x is 1 over x dx. And then to figure out what my dv is, I cover up that, and the rest of this is all dv. So x squared dx is the dv. And then to figure out what v is, I just need to take the integral of this. So the integral of x squared would be 1/3 x to the third. All right. Now I'm going to go ahead and use my formula. So I already have the integral of u dv, that's this part right here, equals u times v. So that's going to be ln x multiplied by 1/3 x to the third, and I'll go ahead and put that in front because it looks less weird, minus the integral of v times du. All right, so now I'm going to cover this up, And this is what I'm dealing with over here. So that leaves me with 1/3 x to the third ln x minus, I'm going to go ahead and take this coefficient and move it to the front of the integral. So now I've got x to the third multiplied by 1 over x, and that would just give me x squared. And so I can go ahead and integrate this. This would leave me with 1/3 x to the third plus c. And I did have that negative 1/3 in front of there. And then I still have this 1/3 x to the third ln x in front of that. So as my final answer, that gives me 1/3 x to the third ln x minus 1/9 x to the third plus, I can distribute that negative 1/3, but that's still going to be a constant. And there's my indefinite integral right there. All right, let's go ahead and do our third example. So here we're going to use a definite integral this time. So we're going to evaluate this from 0 to 1. And we are doing sine inverse of x dx. And when I looked at this, I was like, oh, surely that's going to be on the yellow sheet. And if you look on the yellow sheet, it's not. They don't have any of those inverse functions. So on the yellow sheet, I can see actually that the only thing we know about inverse functions is what their derivatives are. And that's what makes this integration by parts a good option to use, because when you do integration by parts, you recognize what your u is. So in this case, it would be sine inverse of x. And then you take the derivative of that. So I don't know how to integrate sine inverse, but I do know how to take the derivative of that, and this process allows me to use that. So the derivative of sine inverse is 1 over the square root of 1 minus x squared. All right, the other thing that we have is, if you look on your notes, when we do that acronym LATE, inverse trig was one of the ones that we knew we had to use for u. So that was the other reason you might know. But that's how you need to do this. Okay, so there's our u. dv is just the rest of the problem. So sine inverse of x, that takes care of all of it. So that means that dv is just dx, or you can write 1 dx. So the antiderivative of 1 dx would just be x. Okay. So now I'm going to go ahead and use that formula. We've got the integral of u times dv, this is already written out, equals u times v. So that's going to be sine inverse of x multiplied by x. I'm going to go ahead and put that in the front. Subtract v times du. All right, so I'm going to go ahead and clean up this side a little bit. I've got x sine inverse of x minus the integral of x over the square root of 1 minus x squared. And when I look at that integral, I am looking here to see that's an x squared. And this is an x that has one exponent lower. So this is a U-substitution problem right here. This one we can do U-substitution on pretty easily. So I'm going to say my u is 1 minus x squared. That means that the du is negative 2x dx. I can see the x in the problem. I don't see the negative 2. So that means I'm going to have to divide that negative 2 out. So we have x sine inverse of x minus, I'm going to take a negative 1/2 to put in front of that integral, and then I am integrating 1 over the square root of u. Now this, when I integrate this, I'm going to go ahead and make that a plus 1/2. I'm actually integrating u to the negative 1/2 power. All right, so I'm going to go ahead and add 1 to that. That's positive 1/2. I'm now dividing by positive 1/2, which is the same as multiplying by 2. So that means that this is just going to be the 1/2 and the divide by 1/2 cancel each other out. So that gives me u to the positive 1/2. I'm not going to put a plus c on the end because this is a definite integral that I'm evaluating. So now I can go ahead and replace that u again. This is a square root because it's u to the 1/2. What I had for u was 1 minus x squared. And this is being evaluated from 0 to 1. Okay, so I've got 1 sine inverse of 1 plus the square root of 1 minus 1 squared. And I'm subtracting off 0 times sine inverse of 0 plus the square root of 1 minus 0 squared. All right, so for this one right here, I have to kind of picture the unit circle. And I'm going to picture anywhere sine, or the y-coordinate, is 1. So that would be up here. That's where the y-coordinate is 1. That's at pi halves. So sine inverse of 1 is pi halves plus the square root of 0 minus the square root of 1. And so that leaves me with, if I evaluate that, that leaves me with pi halves minus 1. Now, when you're doing problems like this, we know how to integrate this on the calculator, like to evaluate it. So go ahead and go back and check your answer and just make sure that the decimals match. All right. Last but not least, number 4, we're going to go ahead and integrate x squared sine x dx. So if I remember late, then that means that my u is going to be sine x. My du is the derivative of sine, which is cos x dx. That means if I cover this up, the rest of this is going to be my dv, which is x squared dx. And that means that v is going to be the integral of this, so it's 1/3 x to the 3rd. All right. So let me go ahead and use my formula. I have u multiplied by v is sine x times 1/3 x to the 3rd minus v times du. Okay, so now that means this is what we're working with. The unfortunate part about this problem is that if you look at this, this is not easy to integrate. This is another integration by parts. We have like an integration by parts within an integration by parts. So what I'm going to do so that I can keep track of the math that I'm working with right now. You guys don't hate me. I wrote all this down and then I looked at the note on my notes that I'm copying and it said don't use late because the problem never ends. It just keeps going and keeps going. So go back and erase that. I'm sorry, don't get upset. I'm sorry, no one's more upset than I am. Don't argue with me. I'm upset. I'm upset too. I'm sorry. I'm sorry if you use pen. Oh goodness. Okay. Instead of using u for sine, we're going to use u for x squared. Tomorrow I'm going to talk about a different method for doing these problems, and you will see when we do that how you would have recognized that you should use the x squared on this and not the sine. I apologize. I'm really, really sorry. The derivative of x squared is 2x. Okay. So if we take that, that means that the rest of the problem is the dv. And the integral of sine is negative cos. Okay, so again, formula. You guys hear how sad my voice is because I feel bad. So I've got x squared times negative cos x minus the integral of negative cos x times 2x dx. Okay. Whew. All right, now, even though I had messed it up before, what I was saying is still true, that when you look at this, this is still another integration by parts problem. So what I'm going to do is I'm going to kind of color code this, that we're about to do this separately in a different color, except I'm going to go ahead and take this negative out of here. All right, so now I'm going to do this in red. So I'm doing the integral of 2x cos x dx. And again, I'm going to use the u for this part because if I use cos x, this problem will never end. So I'm going to say u is going to be 2x, du is going to be 2 dx. dv is going to be the rest of the problem, so that's cos x dx, and v is the integral of cos, which is sine x. Okay, so if I use my little formula, then that gives me u times v, so that's 2x sine x minus the integral of sine x times 2 dx. Okay, so here's what I'm going to do. This is the original problem, and then I just know that my red stuff is actually this stuff down here, so I'm going to write this out. I've got negative x squared cos x plus, and then instead of writing this, I'm going to go ahead and write all the stuff that equaled. So plus 2x sine x minus the integral of 2 sine x dx. And I can go ahead and put that 2 in the front of my integration sign. Okay, so this gives me negative x squared cos x plus 2x sine x minus, the antiderivative of sine is negative cos, and so that's going to make this a plus 2 cos x plus c.